So, welcome back. Now it's the second class of our course, and in this class we're talking about radioactivity. What's radioactivity? What makes nuclei radioactive, and all this kinds of stuff, right? So, we're starting at probably the most well-known equation of all physics, right? It's on hats, it's on t-shirts. E equals mc squared. Famous Einstein equation. Okay, we all know this equation, but what does it really mean? I mean, there's a mathematic trick here. We have an equals. Equals means that this thing here is exactly the same of this. It doesn't mean that it's similar, that it's almost the same thing. It's exactly the same. And now comes the trick. We have then energy equals mass times c squared. C squared is a constant. It's the speed of light in vacuum, right? So, what it means is energy is the same thing as mass, differing only on a constant, right? That's what it means. This equation means that energy is the same thing as mass and vice versa. It also means that you can translate energy into mass and mass into energy, right? And okay, why is that so important? This is the equation essentially, right? E equals mc squared, where m is the rest mass, for all purposes, mass of something. E is the energy, and c is speed of light squared and everything. So it means that energy can be turned into mass and vice versa, right? If we think about the energy equivalent to one mass unit, atomic mass unit, we do the math here, so we have speed of light squared and everything, and doesn't really matter, as I told before, and I hope you make it have it clear. In this course, we're not talking joule, we're not talking of these usual energy units, because we don't want to be carrying those 10 to the minus something or 10 to the minus a lot. So, okay, if we take a look, let's see how much energy is equivalent to one atomic mass unit. If we do the math, it's essentially one atomic mass unit, if we could turn it into energy completely, would release 931.5 million electron volts, right? So one mass unit could be turned into 900 mega electron volts. As a consequence, if you think, okay, if this is number of MeVs that equivalent to one mass unit, so sometimes we use the unit electron volts per c squared, or mega electron volt per c squared as a unit of mass, because if energy divided by c squared is mass, right? Why do we do that? It's essentially very simple. There's no practical way of weighting very, very small masses. We cannot, it's impossible for us to have a scale and just weight one atom or a molecule. But we can measure energies very precisely. So, most of the times when we're talking about elementary particles, atoms, nuclei, what we really measure is energy, right? So, what better way to translate that to mass than using just dividing by c squared and having the same. So if I measured 931.5 mega electron volts in my system, I know it's a mass of 931.5 mega electron volts per c squared, right? Much more practical. So This is a unit we'll see often over and over again. Just to take a look, what's the rest energy of one electron? Meaning, if I could take one electron and transform it completely into energy, what would happen? How much energy are we talking about? Just doing the math here, and we see the mass of one electron is equivalent to 0.511 mega electron volts. Or the mass energy would be this, or as we more often use in the lab, 511 kilo electron volts per c squared. Well, in fact, nature does strange things. Later in this course we'll see that yes, electrons can be transformed into energy completely, and this 511 kilo electron volt number will come up again, right? So okay, now we were talking about earlier how atomic mass unit was defined as 1/12 of the mass of carbon-12. Okay, and then I just ended last class with a small bit of food for thought. The proton weighs something like 1,007 atomic mass units. The neutron is something like 1,009. So both are slightly weight slightly more than 1. So if I put 6 protons and 6 neutrons together, I would reach a number larger than 12, right? But by definition, I'm telling you that the mass of carbon-12 is exactly 12, right? Or let's get here deuterium. Deuterium, if we look at 1 proton, 1 neutron. And here's the mass of deuterium. And then we put, okay, this is the mass of the proton times the atomic number, which is 1. Here's the mass of the neutron times the number of neutrons, which is 1 also, and then we sum it and then subtract the mass of the deuterium itself. And we discover that the deuterium weighs more than 2 mega electron volts per c squared, less than the sum of its constituents. Right? This is what we call mass deficit, which is essentially. So, first of all, this is very common. You'll see this over and over again. The nucleus weighs less, and in fact, this is a fact for all known nuclei. The nucleus weighs less than the sum of its constituents, right? This difference, just the z times the number of protons, z times the mass of protons plus n times the mass of neutrons, meaning this here is the sum of all the things that went into building this nucleus, and here's the mass of the nucleus itself. So if this is positive, it means that the things you put there weight more than the nucleus itself, meaning some energy just disappeared, some mass disappeared. And where did this mass go? Because we know from energy conservation that this cannot be. Energy cannot disappear. So where did this go? Well, if we take this is essentially, if you translate this into energy, this is the binding energy of the nucleus, meaning this is the energy that was released when the nucleus was put together. So here I have 1 proton, I have 1 neutron, and I just glue them together. Some energy will be released. And we know that because we will need to give this energy back if we want to take this back. This energy that was released is the mass deficit, right? Because when we put things together, some energy was released, meaning some energy was lost by the nucleus, right? And remembering that mass and energy are the same. If we want to conserve energy, we think conserve mass plus energy. If I eliminated some energy, I diminished the mass of this. So essentially, the mass deficit is the binding energy of that nucleus, right? So to determine the binding energy, we will do Z times the number of protons times the mass of the proton. The number of neutrons, remembering that the number of neutrons is the total number of nucleons, which is the atomic mass, minus the number of protons, right? This is protons plus neutrons. If we subtract protons, we're left with neutrons. So we have number of protons times the mass of the proton, number of neutrons times the mass of the neutron. And then we subtract the mass of the whole beast together, right? This is the mass that was disappeared when the nucleus was assembled. And so if we multiply this by c squared, we have the binding energy, meaning the energy that is keeping all those things together. And as we expect, okay, this will grow quickly when we increase the atomic number of everything, the A. More nucleons, more binding energy. But more meaningful than that is how much is the binding energy per nucleon, meaning how much is the energy that is keeping each one of those glued together. If we do that, we get the binding energy and divide by the number of nucleons, which is the atomic mass, number of mass, right? So this we call binding energy per nucleon, which is essentially a measurement of how bound is that nucleus. Then if we take a look at this, here we have binding energy per nucleon, and here atomic number. If we take a look, we see that, well, of course, hydrogen 1 is not here because there is no binding energy in something that is only a proton. But you see that it grows quickly, right? So the deuterium is down here. You start to increase the number of nucleons. You increase a lot the binding energy per nucleon until you reach something like iron or something around here, tin, and then you got the highest binding energy per nucleon you can, meaning that this is the most bound nucleus we have, right? When we keep increasing, then binding energy starts to drop. The idea here is rather simple. You start to increase nucleons. You have more things to glue together. You increase the number of things that are attractive, and then you increase the binding energy, right? If you got some magnets, for instance, you have this, you just put those small round magnets, right? Spherical magnets. You put two together, okay, you can separate them. If you put four together, they get much more tightly glued together, right? And this goes up to a certain point, because over that point you start to have too many nucleons together. And remember, I told you that the nuclear interaction, it's so short-ranged that if you think classically, we have an amount here, the magnets. This magnet is not feeding the magnets on the other side anymore. It's just feeding its neighbors. And so after it gets of a certain size, adding more will not increase the binding energy. And on the other hand, the protons are still repulsing themselves. So you start to have repulsion starts to win the war. And so binding energy per nucleon starts to drop. What can we say when we look? One thing that's important to see is that helium-4 is very high, is an outlier very high here, right? This has consequences later. What we can look at this and say, okay, helium-4 is a very, very tightly bound small thing, right? What we have then, the idea is if we merge two light nuclei, forming a heavier nucleus, we will have release of energy, right? Because those had lower binding energy per nucleon than the other one. Nucleons didn't disappear. So all of a sudden you increased your binding energy per nucleon, meaning you release a lot of energy when you do that. This is what's called nuclear fusion, right? You may have heard of the attempts to make electric energy from this. That's the concept. You get two light nuclei like helium and hydrogen, you put them together, you will produce a heavier nucleus, usually helium-4, and it will release a lot of energy. This is also the process that goes spontaneously on the production of heavy nuclei on nucleosynthesis, right? Because you have on a star, you have a lot of hydrogen that's burning and becoming helium, and helium becomes carbon, and that's how it goes. All because those reactions, they release energy. Another consequence, as you see, if I have a very heavy nucleus here and I break it in two pieces, I increase the binding energy per nucleon too, right? So if I do that, I release energy also. This is what's known as nuclear fission. Fission meaning breaking. So nuclear fission is essentially a way to get a heavy nucleus here and release energy by breaking it into pieces. That's the process that takes part on a regular nuclear reactor and on a nuclear explosive device of some kind, right? So, okay, let's go on and take a look. This is essentially the same image there, turned down. And we have here, if you see, the highest binding energy per nucleon, meaning the lowest excess mass. You have here a valley that forms, right? So this is just like a regular valley. Every nucleus that's outside the valley, it wants to fall down to the valley. Meaning, we call this valley of stability. Meaning that nucleids which are away from this, they want some way to get down here and be on this path. There's not, but this is like playing chess. You cannot move your pieces the way you want them. There are rules for that. And that's what radioactive decay is. It's essentially nuclei trying to find a path to go down to this valley of stability. So, a bit of history again. In 1896, Becquerel noticed that uranium salts, they emit radiation which is similar to X-rays, which were discovered by Röntgen the previous year, impressing photographic plates. And he noticed one other thing. The emitted radiation was proportional to the concentration of uranium, meaning that it should have something to do with uranium itself. And he also noticed that this radiation is independent of pressure, temperature, or chemical form, meaning that this radiation seems to have nothing to do with electronic form. It seems to be related to the nucleus itself. And 2 years later, Pierre and Marie Curie, they noticed that thorium emits the same radiation. And also doing some studies, they discovered polonium and radium, which were even more radioactive. And that's where the term radioactive comes from, because radium emitted much more of this radiation, in the same mass of radium emitted 10 times more radiation than the one of that mass of uranium, and thus radioactivity. Okay, so just a curiosity, nothing really, but sometimes it's nice to see things. This is the first known X-ray photography. Probably there were others before, which Röntgen did for his own studies, but this is the oldest one we have seen, which is from Bertha's hand. Bertha was his wife, and he did this to show her he was not crazy. So you see the bones, you see the ring, but you don't see the flesh, right? And just one more curiosity, on the early times, no one knew radiation would do any harm for you. So radiation was the big thing, and well, in fact, they used, even shoemakers would use it. You would have a small X-ray machine you put your feet on, and it would show how is your foot placing inside the shoe, to see if you're forcing your foot to the wrong position or anything, right? Of course, later they discovered X-ray radiation was bad for your health, and then they decided this was not a good way to do things. But in fact, well, coming back to radioactivity. So Paul Villard, this is what's known, I forgot the name of the experiment, but anyway, there's a way to differentiate different decays. What do? We have a lead shield, because it was already known that lead would block all radiation. So you have a lead shield with a small hole and a sample of radium inside. Then you have a small target, which is made of an outer paper wrapping. You have two photographic plates and a small piece of lead between them. Very thin piece of lead. What they noticed was, I think it's Rutherford's experiment. This one, the alpha, and you applied more than that. You applied an electric field here between this. So what they noticed were there were particles. They call them alpha particles, which were pushed towards the negative. Say we have the negative plate up here, the positive plate up here. So it was clearly positively charged, and it was blocked very quickly on the outer paper wrapping. You had to remove the wrapping to have any signal of it. You had another kind of radiation that by the curvature you could tell it was lighter, and you could tell it was negative because it leaned towards the positive plate down here. It would go okay through the paper wrapping, but it would stop on the first detector. On the first emission, it would not be able to cross this thin lead shield here. And there was a third type, which would pass through both detectors. It would leave some marks in both, but it clearly could escape if you put another plate here, would be a sign anyway. And it didn't seem to be reacting to the electric field. So they called the first one alpha, and it was clear that alpha particles were positive and heavy. There was beta, this one they called it beta particles. It was clear that they were lighter than alphas, they were negatively charged, and they could penetrate matter a bit more. And the third one, they called them gamma, because it was seemingly unresponsive to electric fields, so it shouldn't have charge, and was really deeply penetrant, could penetrate anything. Right, so this was discovered by Paul Villard, and now we have the three main radiations we talk about essentially. Alpha particles are heavy and positive. Beta particles are lighter and negative. And gamma is just electromagnetic radiation, so it's really, really light, no real definition of weight, and have no charge. Right? And so here we have the three distinct types of radiation in a nutshell. Alpha particles are helium-4 nuclei. Remember, I showed you that helium-4 was a very very strongly bound small piece of matter. That's why matter, when trying to eject things from a nucleus, they tend to form alpha particles. It requires less energy than emitting, for instance, a single proton or a single neutron. So the alpha particle is a helium-4 nucleus, meaning it's 2 protons and 2 neutrons with no electrons. It has positive charge, 2 plus, and it's highly ionizing, meaning it interacts very strongly with matter, so it is stopped quite quickly. Beta particles, on the other hand, are electrons with very high kinetic energy. Very high meaning the speeds they are into are on the order of magnitude, are very close to the speed of light in vacuum. Right? They have negative charge, they are electrons, so negative -1, right? And the gamma particles are very energetic electromagnetic waves, meaning photons. They have no charge and they are part of the electromagnetic spectrum. We show more here. So if you look at the electromagnetic spectrum, we have radio waves on the 1 hertz, on 1 meter scale. If we go up, we reduce the wavelength, increase the energy, right? So we have microwaves, which are related to molecular rotations. That's how microwave heats your food. Then you have infrared, which has to do with molecular vibrations, not rotations. And the upper infrared start to have something to do with valency electron transitions, meaning you can get the outer electrons in an atom and somehow excite them. Then you have the visible light, and you have the ultraviolet light, where valence electrons start to get kicked off the atom, thus leaving it ionized and everything. Then we have X-rays. X-rays have to do with electron transitions. So X-rays, they are emitted in electronic events. And you have gamma radiation, which has to do with nuclear transitions. Now you may notice there's an overlap here between X-rays and gamma radiation. This is tricky because you have high energy X-rays, can reach up to 100 kilo electron volts or more, and gamma radiation, which is typically of millions of electron volts, but you have very low energy gamma rays from 4 or 5 kilo electron volts up. And we have here an issue, because you know what's the difference between an X-ray and a gamma ray? None. The only definition, you'd call an X-ray if it was emitted in an electron event, an electron that is promoted and then goes back to the fundamental state or something, and you call it nuclear. We call it gamma rays when it comes from nuclear events, meaning it has to do with events that took place on the nucleus and not on the electrosphere. But if you have, say, 87 kilo electron volt photon here, you cannot say if this came, there's no way at all to say if this is an X-ray from lead or if it's a gamma ray from something else, right? Okay, so once again, Rutherford experiment, just to have you know, right? The alpha particles, they are bound, they have positive charge, so they go towards the negative side of we have an electric field here. It's not represented, but we know it there is because there's the curvature. Beta particles, they go the opposite way because they have negative energy, and you see they bind, they really turn a lot more because they are lighter. and the gamma rays go straight. Okay, so now let's talk about what is radioactivity. We have nuclei which are stable, they are on the stability valley, everything is okay. But what happens when they are outside this stability value? If they want to stabilize, to get stable, to reduce their energy, because in nature things want to go to the lowest possible state in energy. It has something to do with the second law of thermodynamics and everything. So every time any physical process happens spontaneously in nature, it tends to take you to a state where order is diminished, where you have less in energy. For instance, you want to, every time a process happens spontaneously, it wants to increase the binding energy and release energy for the universe, right? So energy starts to be packed into this very small thing. These very small things, you reduce the mass of the universe and you release this as energy. That's how things go. They never go the opposite way. You never have things getting heavier and absorbing energy. It can happen in very specific processes, but they will release that energy excess again, right? So we have two kinds of nuclei. We have the stable ones, which are in the stability valley, and you have the ones that have excess energy, meaning there's some way their mass can be small, or their binding energy per nucleon can increase. This excess energy can be released in two ways. Either in the form, if it's only on an excited state, if it's if it's just an isomer of the original nucleus, it can emit only gamma radiation and it's okay, it just gets rid of the excessive energy. But most times it's already in its lowest possible energy state, and still there's ways to reduce it. How can we do it? By emitting particles. So the nucleus may emit either alpha radiation or beta radiation, and this way become another nucleus with higher binding energy per nucleon, right? So nuclei always tend to seek more stable configurations. As I told you, they want to be in a stable condition and release its excessive energy for the universe to use. That way you could almost think of a nucleus as a socialist. It wants energy to be available for the most and not only for him. But this means it has to emit radiation by doing that. If we have a nucleus that has excess of protons, of course it can decay by alpha radiation, which we have already talked about. We will reduce 2 protons and 2 neutrons and you take it to a more stable situation. But there's another thing we didn't talk about until this moment. I'm sure we're all familiar with the very broad, at least broadly, with the concept of antimatter, right? So every particle has its own equivalent in any matter. Its enemy, its fundamental enemy, if you want, whatever. So the electron has its antiparticle, which is the positron. It's just like an electron. It's equal to an electron, but it has positive charge. And if it finds an electron somewhere, they annihilate and become energy instantaneously, right? So nuclei with too many protons, they may emit a beta plus, a positron. Oh, but I told you there was only neutrons and protons inside the nucleus. Yeah, just hold it, we're coming there. For some way it can produce a positron in there and emit this excess charge. And another thing that can happen is the nucleus may just absorb one electron, capture one electron from one of the inner shells, and then reduce its positive charge in the nucleus too, because this electron has -1 charge. Nuclei with excess of neutrons, they don't have those many chances. So what they can do is emit beta minus, which is 1 electron, and then they will eliminate 1 negative charge from the nucleus, become a bit more positive. Once again, okay, there were no electrons on the nucleus to start with, but there's a process where something happens in the nucleus that will produce this electron, right? And if it's just excess of energy, not of neutrons or protons, then you have a gamma ray. So, what is alpha decay? This is simple to understand. If you have a nucleus that has A mass and Z protons, it emits something with 4 of mass and 2 protons, meaning 2 protons and 2 neutrons. It will have 2 protons and 2 neutrons less, so it will become another chemical element with Z minus 2 and 4 units of mass lower, right? 2 protons, 2 neutrons. Okay, so this is the alpha decay. Until now, things are easy. Let's go to the bottom one first. Okay, you have a nucleus which is excited. This star here means excited. It will simply decay to emitting a gamma radiation. No change in proton number, no change in neutron number. It will only go to a lower energy state. That's fine too. Now comes the problem. Okay, if we have something that undergoes beta minus decay, what is beta minus essentially? You have one neutron may become 1 proton plus 1 electron. So when beta decay happens, you will transform 1 proton into 1 neutron into 1 proton, right? So you increase same number of mass because you lost 1 neutron, gain 1 proton, but now the chemical form has changed. It's not the same nucleus anymore, it's not the same chemical species anymore, and you have 1 electron that's traveling. So you see, the electron wasn't in the nucleus in the first place, it was produced there by this phenomenon. Beta plus decay is the exact opposite. The proton becomes a neutron plus a positron. So same thing, same number of mass, because 1 proton became 1 neutron, but it's okay. But now you have 1 less proton, so chemical species went down in 1 unit, right? Have 1 less proton here. And the beta plus. One thing should be noticed in all these cases, and it's always true, charge must be conserved. So if you gain 1 unit of charge in the nucleus, you have a negative charge emitted. If you lose 1 unit of charge in the nucleus, you have to emit this charge, right? And the electron capture, well, the electron will interact with a proton, turning it into a neutron, right? Because we had 1 less charge here, we must have 1 less charge here. And once again, if you see, the outcome is the same of the beta plus, only difference has you have no positron emission in this case, right? And once again, one thing that's important here, I told you in electron capture, it will capture 1 electron of one of the inner orbits, right? In fact, if you take a look here, you will see these are the orbitals. You'll see that every orbital except the S1 have no probability of having 1 electron inside the nucleus at any moment. So just as a curiosity, electron capture can only happen with s orbital electrons, right? So things that you have to keep in mind about radioactive decay. Charge is always conserved. So if I emitted a negative particle, I must have created a positive particle inside the nucleus. If I emit a positive particle, I must have diminished the number of positive particles inside the nucleus. Number of mass is always conserved. In the case of the beta decays, it's explicitly conserved because electrons have mass 0, right? Number of mass is 0. So it just transformed one proton in one neutron and everything. And in the alpha decay, if you see, it lost 4 units, plus these 4 units are in the alpha particle. It's lost 2 protons, which are in the alpha particle, right? But there's one important thing to remember, that when we're talking about beta minus, beta plus, or electron capture, the N and the Z will not be conserved. A proton will become a neutron and vice versa. Just one thing, not really important, not for this course, but it's good to know that these three processes, which are broadly known as beta decay, no matter if it's beta minus, beta plus, or electron capture, they all fall in the category of beta decay. And beta decay is ruled by the weak force. That very weak and very short-ranged force I showed you that would only act inside a nucleon. A nucleon, sorry. So what happens is this strange force there, it will turn a proton into a neutron or a neutron into a proton, right? That's what it does. Now, just to end this class, I'll put some exercises for you. I won't follow step by step. Then if you have some trouble, you talk to me, but let's say I want to know the binding energy of lithium-7. Lithium means 3 protons. So we have here the mass of lithium-7. What happens? The binding energy will be Z. Z is 3 times the mass of the proton, plus N times the mass of the neutron, which I didn't put, I have it here, minus the mass of the atom itself, right? Then you multiply this by c squared, you do the math, you have 39.24 mega electron volts. There's one important thing to note here. You see that here I have the mass of hydrogen 1, not really the mass of the proton. There is a slight difference, very, very small, but it's important to notice. Because when we talk about, you look at the tables, you see the mass of lithium-7. This is the mass of the neutral lithium-7 atom, meaning it's an atom with 3 electrons. It has the nucleus plus 3 electrons. So in order to take this into account, we use here the mass of hydrogen 1, which is the mass of hydrogen plus that 1 electron, right? It's just a way to cancel things out. So the neutron is the neutron, there's no electrons involved. But it's just a way to have these 3 electrons here cancel out with the 3 electrons that now are here. And so we calculate the binding energy per nucleon for the same nucleus, is just to get this energy we got. We have 7, right? Nucleids inside here, and nucleons, and we have 5.61 mega electron volts per nucleon for lithium-7. Okay. Another exercise is, well, the greatest binding energy per nucleon among all nucleids is that of nickel 62. It can be described thus as the most strongly bound nuclide, and the neutral atomic mass of nickel 62. Neutral atomic mass meaning it's here is the weight of the atom plus the electrons. And we want to know the mass deficit in atomic mass units, the binding energy in mega electron volts, and the binding energy per nucleon. So first of all, okay, our old friend here, we just substitute here, and you see hydrogen 1 again to avoid problems with these electrons. And we have then, okay, the mass. This is the binding energy right, which goes up to 500 megaelectron volts, 545 megaelectron volts. And okay, I didn't put the atomic mass deficit here. It's this one, right? If you do the math here, this part is the atomic mass difference in atomic units. And then binding energy per nucleon, you would just divide this by the 62 nucleons we have here, and it's 8.79 mega electron volts per nucleon. This is the binding energy of the mostly bound nucleus in nature. Okay? But then there's one thing I want you to notice here. This is an important thing. If we go all decimal digits on this, and these things usually have 7, 8 decimal digits, we get to this as the, which is what I used here, right? A lot of decimal digits. We get to this as we got on the exercise. But sometimes, for instance, in the exercises and in my test, I'll give you things with 3 or 4 decimal digits only. That's because you don't have to use all this. All those digits will make it easier for you to make a mistake. I don't want you to make mistakes. So, but there's a trick here, and you should be aware of this. If I use only 3 decimal digits, as I would do in a test, you see we get to a very different value for the binding energy and for the binding energy per nucleon. This is not the correct value. Nevertheless, in my tests and in my exercises, I want you to do the math with the number of digits I gave you, just to avoid making mistakes. But if you want to do anything really serious in your work or anywhere, you have to use all decimal digits. Otherwise, you get to very weird places, right? Just to know this. This, in fact, is a consequence of something we call small difference of large numbers, which is essentially what happens when we do this here, right? This is something like 28, this is something like 34, this is approximately 62. The numbers are big, the difference is small, and then the last digits here start to matter much more than we would usually think. Okay, just a quick tip. And that's all for today. Next class we'll talk a bit more about radioactivity. We talk about, okay, we know how, now we understand the energy balance of it, but what about the time qualities of it? How does it evolve with time? What is half-life? Why is this thing important? We're talking about this next class, okay? Thank you for watching. See you next class.